Hi class. All right, this is the beginning of class 5. I forgot to start the tape, so I guess my punishment is I'm going to do a quick intro for class 5. I did notes for this class, actually slides. You can look at them on the Blackboard website under course materials, class slides, class 5 slides. So, in class 5 we talk about regression. I'm going to direct your attention to the bottom of page 1. You can see that I've got a scatter diagram. On the x-axis is time spent online. On the y-axis is money spent online. With regression, we try to establish a relationship between two things. We'll call the x variable, time spent online, the independent variable. So people spend a certain amount of money on, a certain amount of time online, and we are attempting to predict how much money they will spend online as a result of that. So in this example, we've collected 6 pieces of data, and you can look at the dots. You can see, there's each of those represent a person, how much time they spend online versus how much money they spend online. And you can imagine that we draw a line through that data that seems to fit the data. It's not going to be a line that will fit perfectly, but it's a line that will be our best estimate at what that relationship is. Now, what I did in class and what I'm going to do again is I'm just going to preview the key concepts that we will go over in class so you can think about intuitively how that material, the material intuitively, and then what will follow will be filling that in with the numbers and the equations and such. So we're thinking about how we might fit a line in that data. It's not going to fit perfectly, and that's the first key point, is there's going to be some error. So if we were to draw a line through that data at the bottom of slide 1, there would be some points would be a little above the data, some points would be a little below the data. The line of best fit is going to reduce those errors as much as possible, but there's still going to be some error, and we'll call that unexplained variation. It's not explained by the regression line, it's explained by other factors. We don't know what they are. All we know is that time spent online does not perfectly explain how much money is spent online. So that's an error. We don't want to look at just the negative side. We want to look at the positive side too, which is that this regression line that we just drew, that I just drew, all right, I'm going to draw it. And you can print out the slides, you can draw your own. We will look at how much variation there is total, right? Before we even draw our regression line. You can turn to the next page. Actually, yeah, on the next page, top of page 2, there's that regression line that I drew. You can draw to. Bottom of page 2, there's a straight line across, average money spent online. So that's taking the average amount of money that everyone spends of those 6 people. So that's just straight average. And you can see we have deviations from the average. The first dot, as you look on the left side, is fairly close to that average. And if you look over on the right side, you see one that's really high. Right? You're like, wow, why is that so different from the average? Well, what the regression line shows us is it explains some of that difference. So if we were to, without the regression line, just say how much difference each of these points are from that average money spent online, that would be the total variation. So the bottom of page 2 is giving us an example of total variation. And then we look at the top of page 2, we draw our regression line, and we explain some of it. So some of that variation is explained. Like the reason why that dot that is to the far right-hand side is higher than the average is partially explained by the regression equation. So bottom of page 2 gives us a sense of total variation. Top of page 2 gives us the explained variation. But there's still some error. I mentioned earlier, as we find that line of best fit, it's not going to fit the line perfectly. So there's three things. Total variation, get a sense of that at bottom of page 2. The amount of explained variation, top of page 2. And then the fact that that line doesn't quite fit perfectly, unexplained variation. So what we can do later on in the class is we can say the amount of unexplained variation divided by the total variation, that tells us is, say, 10%. So 10% of the data is not explained. 10% of the reason or factors that go into money spent online is not explained by time spent online. Conversely, we can look at how much is explained. And we might have a pretty good regression equation which would explain 95% of the variation. So how much money someone spends online can be explained 95% by how much time they spend online. Okay, so that's step 1. We'll call that performance measures. Step 2, or the second thing we'll do in class, is we'll think about the fact that this is just a sample. These are 6 points of sample data out of a population of, how many online users do we have? 4 billion. So we need to understand that we can't say this is a conclusive, that is the regression line for the whole population. There could be variances. We could have gotten the y-intercept a little bit wrong. We could have gotten misleading data for the slope. So those are the two things. You can see that regression line. 1, where does it cross the y-axis? As we look at the whole population, there could be a problem with the sample data we've collected, so we may need a confidence interval to explain that. Step 2, or the other thing, is the slope of that regression line. That's based on a sample of 6. The whole population, we can't conclusively say that that's what it is for the whole population. We need a confidence interval to account for what the slope of the regression equation for the whole population would be. With that, we will do a hypothesis test to test whether or not the slope is significant, whether or not it tells us something significant. Now in this example, we're saying that the time spent online has a positive relationship to the money spent online, meaning the more and more time a person spends online, the more money they might spend online. So that just means that the line, the regression line, top of page 2, is sloping up as we move to the right. So we think there's a positive relationship. But when we infer that sample data on the whole population, we can do a hypothesis test where we'll assume there's no relationship. It's just a straight line. That will be our null hypothesis. No relationship between time spent online and money spent online. And if you remember from class 4, the alternative hypothesis will be something that we will need overwhelming evidence to prove. So null hypothesis, no relationship. If we find overwhelming evidence that there is a positive relationship or a negative relationship, then we will reject the null and say, oh yeah, there's a significant relationship. Okay, so that's the second section of material we'll cover. The first was performance measure, variation explained. The second was what we infer from the sample data on the whole population. Third was the expected values for y in the whole population. So in addition to the fact that we've just taken a small sample and we need a confidence interval for the whole population, there's also something else. The population of internet users has variation within itself. So of all the people who spend, say, 15 hours a week online, they don't all spend the exact same amount of money online. In fact, I'll just skip ahead because it's easier to do when I'm not doing the PowerPoints. I'll just skip ahead here to the bottom of page 12. This is when we get to the inferential side of regression, what we infer about the whole population. You can see that we've got x on the horizontal axis, y on the vertical axis, and we've got data. Let's just assume it's time spent online on the x-axis, money spent online on the y-axis, and you can see it's moving up as we move to the right. Now that line, the actual line in between all those dots, that is the exact specific regression equation for the whole population. But those dots, those are the whole population. The dots don't conform exactly to what we would expect or what we would predict as the expected value for the regression equation. And that's the way it is. Two people who spend the exact same amount of time online, they do not spend the same amount of money online. And the issue there is there's just other factors affecting it. It may be income, it may be how impulsive the person is. So if we're going to estimate how much time does Carlos spend, if we're going to estimate how much money does Carlos spend online, if he tells us how much time we spend online, then we can tell, we can determine some part of the answer to that question, but he could be any of those dots. Okay, so that was the third part. First part was performance measures. The second part was what we infer on the whole population once we look at the sample data. And the third part was related to that inference, but it was just to remind you, make you aware that there is no exact y value that will be outputted if we input an x value, because different people spend different amounts of money, even if they spend online, even if they spend the exact same amount of time online. Okay, I feel like that took a lot longer than the introduction in class. Hopefully it was useful and not confusing. So let's direct our attention then to the bottom of page 3. Simple linear regression means one independent variable, one dependent variable. Linear means there's a straight line relationship. There are other types of relationships, but we'll just look at a straight line relationship. And today we'll look at one independent variable, one dependent variable. Next week, we will look at multiple independent variables. So there could be several things determining how much money you spend online. It could be how much time you spend online. I think I just said this like 2 minutes ago, but how impulsive you are, how much money you make, how embarrassed you are when you have out-of-style shoes, all those different independent variables which will spit out money spent online. That's multiple regression next week. Performance measures, that's the explained variation, unexplained variation. Inference, which is what we infer in the population. Estimating the intercept and the slope, that's again inference. So if we have a sample, we may have gotten the slope or the intercept wrong, and so we need a confidence interval for that. Furthermore, we can do a hypothesis test to see how confident we are that there is a meaningful slope, that there's a slope that can be represented statistically. And then estimating values of y. That's that thing I mentioned with the estatements and how people are different. And then the last thing, complete printout for simple linear regression. Actually, I forgot to do this in class. But I will tell you the page number. All right, the printout is on page 425. So you can look at page 425 and you can see how the printout works for everything that I talk about in this section of the video and the class section video. Essentially, you don't have to come to class, you just need to look at that printout. That is an exaggeration. You need to come to class so you can understand what that printout means. but you won't have to do the calculations because you can look at the Excel printout. Okay, moving on to page 4, regression. That's a definition. Regression analysis attempts to identify a mathematical function that relates two or more variables so that the value of one can be predicted from the value of other. Value of how much time you spend online can be predicted. Value of how much money you spend online can be predicted by how much time you spend online. Simple means one independent, one dependent. I talked about that. Multiple is one independent. Multiple would be two or more independent variables. We'll do that next week. Straight line means linear connection. You got it. Bottom of page 4. Once we take a sample, we will be able to calculate the slope and the y-intercept. And we will be able to calculate an equation. Y equals A, which is the intercept, plus B, which is the slope, times X. So we will input X into that equation, and it will spit out our predicted value for Y. So we will input time spent online, it will spit out money spent online. And take a look at that slope B, recall from algebra. The slope is the change in Y for a 1 unit change in X. So 1 more hour spent online means $3.50 more spent online. So you spend an extra hour online, you spend an extra $3.50 if the slope is 3.5. Okay, let's move on to page 5. Basic simple linear regression. Basic concept. Simple linear regression uses one independent, one dependent, produces a straight line. Indicates to what extent the variables are associated. It does not show cause and effect. This is one thing statisticians get really funny about. We cannot say that the amount of money you spend online is caused by the amount of time you spend online. You can only say that there's a correlation between those two. Or you can say that we can predict money based on time spent online. But we can't say there's a cause. We need to think that through carefully before we even try to make a statement like that. Statisticians don't really get into cause and effects as much. But the data can be very powerful and very useful even without being able to say the cause and effect. Scatter diagram, which is the diagram we used in the previous slides. We'll plot everything, fitting a line to the data. All right, so we talked about this. Generally, the data will not fit the line perfectly, but we'll do the best fit. All right, so bottom of page 5, we are ready to get into the performance metrics. So we've got our same scatter diagram. We're going to find that line that makes the sum of differences from the line 0. So take a look at the first point. As you look to the left, it's a little bit higher than the line. The second one, as you move to the right, it's just a tiny bit lower than the line. So maybe the first one is like +3. Maybe the second one is -1. So now we're at like 2. And then as we keep adding those up, the line of best fit is going to sum to 0. Yes, it is possible that that line, the deviations from the line in the sample data, will sum to 0. What we want to do as statisticians is, instead of having data that sums to 0, is we want data that tells us something more useful. So we are going to square all those variations. So they don't cancel each other out and just equal 0. The squares tell us the magnitude of the variation. For example, we could have data that's really high and it could be canceled out by a data point that's really low, and that would be more variation than 2 data points that are just one above, one below. They both sets of data sum to 0, but if we square the differences, that gives us more meaningful information. And we're going to call that the least squares criteria. We call it later the sum of squares error, SSE. Later on, SSE. For now, we'll just call it the least squares criteria. I'm at the top of page 6. Identifies the best fitting line as the line that minimizes the sum of the squared vertical distances of points from the line. Okay, so we want that as small as possible. what we will later call the sum of squares error. So errors, how much above or below the line they are, squared, add that all together. We want that as little as possible. And if we didn't square them, remember they would all add up to 0. Okay. Now, bottom of page 6, we have equations based on, say, these 6 points of data or 4 points of data. We could calculate the least squares criteria, and we could come up with the slope. And those would be the equations at the bottom of page 6. So it's the slope b equals n, number of samples, times the sum of x times y. So every x times every y, sum it all together, minus the sum of all the x's, so add up all the x's, sum of all the y's. I do all this towards the end of class, so you can just look at it there, but it's just put the numbers in Excel, add them together, or multiply when you need to. I recommend that you do this once or twice with Excel just to get a feel for where these numbers are coming from. And then after that, you'll just read the printout and we'll never calculate it again. So we have equations where we can calculate the slope and equations where we can calculate the intercept. All right. Once we do that, and we're at the top of page 7, we have an estimated regression equation. So y, that little hat, little thing above y hat, we call that y hat. That's the predicted value for y given some value of x. So you tell me how much time Joey spends online, I will tell you the predicted amount of money Joey spends online. And that's y hat equals a, which is the intercept, plus b, which is the slope, times x. So you enter x, I multiply that by the slope, add a to it, boom. Okay. So I guess we're still warming up here, intro to simple regression. Now we're getting into the specific performance measures. And remember I said that was explained, unexplained, that type of thing. So bottom of page 7, we went over, I guess we didn't go over unexplained. I guess we did, we went over like some of the data is explained by the regression equation, some of it is not. So unexplained variation, 2 down we have explained variation, 3 down we have total variation. And it turns, and so when we calculate the ratio of explained to total, we get the coefficient of determination. So if the explained data, sum of squares is like 490, and the total variation of sum of squares variation is 500, so 490 over 500, that's like 97, 98%. You would say the regression equation explains 97%. Another, and we'll talk about that more. Another important metric is the correlation coefficient, which is the square root of the coefficient of determination. And with square root, it can be positive or negative. So we'll say that there's a positive relationship or a negative relationship once we look at the correlation coefficient. And with the example we used earlier, we were thinking that there was a positive relationship. So more time spent online equals more money spent online. It could be negative. More time spent online could mean less money spent online. Like people who spend their whole lives online never buy anything. They just stay at home and surf the internet. Or maybe there are people who know how to find deals because they spend so much time online, so they spend less money online. So that would be a negative relationship. All right, and the only other thing I didn't mention at the bottom of page 7 is going to be the standard error of the estimate. This is going to be our basic standard deviation term for the line of best fit that we calculate based on the sample data. So we'll have our sample data, we'll calculate that line, and we know that it's not going to fit the data perfectly. There are some variations. So we're going to use that sum of squares error, and we're going to divide by some number and take the square root of that, which is going to give us our basic standard deviation based on this sample deviation. Standard error of the estimate. I think we explain that. I explain that more carefully. All right, so here we are. I'm 24 minutes in. I'm at the top of page 8. Take a look. I want to do this. So we're top or bottom of page 8. I haven't decided yet. So, okay. Yeah, let's look at the top of page 8. Okay, so we have 6 points of data. There's something represented on the x-axis, something represented on the y-axis. Now that straight line that has y with a bar over it, that's the average y value. So if you can say, look at that first point, it looks like it's about 1, 2, 3, 4, 5 notches up, and that's the average. The second point is 2 up. The third point is 5, 6, 7. The fourth is like 3 up. So we just add those all together and we average them, and that's going to give us that straight line, y bar, y with a bar on top of it. That's the average. The line that is sloping up to the right, it has a y with a little hat on top of it. That's y hat. That is the regression equation that we're going to calculate based on previous formulas. So let's look at that point of data at the highest one. It's the almost as you moved from left to right. It's almost to the far right, but it's not quite. It's the highest point of data. So the difference between that and the line labeled y bar, that is the total variation. Now, if you were just taking a straight average of, say, money spent online, that could be the y bar. And you'd look at that really high point of data and say, gosh, why does that person spend so much money on why is that person so high above the average? Well, we can explain part of it with the regression line, y hat. You can see that the regression line is closer to that point of data than y bar. So the part between the y hat line and the y bar line, that is explained. Explained. The part above the y hat line and all the way up to that point of data, that is unexplained. Unexplained. That is summarized on the slide below. The long line is total variation. The one between y bar and y hat, which is y hat minus y bar, that's explained. That's what we predict from the regression equation. Above that is unexplained. Right? That's variation over and above what we would expect based on our calculations of the regression equation. Okay, let's take a look. Top of page 9. Here we have the sum of squared error. Now I mentioned that we call this sum of squared errors, sum of squares error, earlier when we were using the least squares criteria to calculate, when we were using the least squares criteria to calculate the line of best fit. So that is unexplained. Okay, so that's unexplained. Let me backtrack a minute. I remember I did something in class before I confused you online. So, okay, let's just go back to the top of page 9. So we've at the bottom of page 9. So we've got the total variation. Is that, you know, yi, which is an individual value for y, minus y bar. And then we've got explained variation, which is y hat minus y bar. And above that, we've got unexplained variation, yi minus y hat. Okay, so a very important metric is how much of the difference, how much of the variation can be explained with the regression equation. We will find that by taking the explained variation divided by the total variation. Okay, you with me? Explained variation divided by total variation. Let's skip ahead to the top of page 11, and that's going to give us our coefficient of determination. also known as r squared. So explained variation divided by total variation. Okay? I just want to jump ahead and make sure you're clear on that before we move on. Explained over total is the coefficient of variation. Again, I think I used an example. If our sum of squares for the explained variation is 490 and our sum of squares in the total variation is 500, 490 divided by 500 gives us like 97, 98%. This regression explains 98%. Okay. So we are back to the top of page 9. And then, I'm not sure how much I stressed this in the video so far, but so the sum of squares error, I think I remember talking about it in the video. So that's the error. The line doesn't fit perfectly, so there's a little bit of a difference between the data points and the actual line. We square that, we sum it all together. And then let's skip the bottom of page 9 for a minute. And then let's look at top of page 10, sum of squares regression, which is how much of the data is explained by the regression. We add that all together. It's just the y hat minus y bar. And you can look back, y hat minus y bar, it's that explained. We square that for every data point, add it all together. It gives us how much data is explained by the regression. And then the same thing, bottom of page 10, sum of squares total, which tells us, from the actual y to the average y. So find that difference, add it all up, square it for everything, and that's going to give us total variation. So we've got total variation, we've got explained variation, we've got unexplained variation. And then I think it picks up the video you're about to watch. Picks up with standard error of the estimate, which is our basic standard deviation term for the regression line. So have fun watching that, and I will see you in class. Okay, so starting the recording just a little bit late. Where are we? We are with the sum of squares error, and we're gonna all right. All right. You've heard me say this like 6 times before. We use this a number of ways. 1, to find the line of best fit. 2, we put it in the coefficient of determination, find the percentage of explained versus unexplained. And the third thing, which we haven't gone over yet, is we're going to find the standard deviation metric for that regression line that we create. Let's do that. Let's call it standard error of the estimate. So this is the line we put in. How well does it predict based on the sample data? Well, let's look at how much residual error is left over. So let's take that residual error, let's divide by n minus 2, and let's take the square root of that. And that is going to give us standard error of the estimate. Standard deviation type measure that measures the dispersion of the data around the estimated regression line. Dividing by n minus 2 reflects the fact that there are 2 coefficients, which is the y-intercept and the slope, that are being estimated. So there's more missing data that we are trying to estimate. 2 things, in fact. This the y-intercept and the slope. And this can be affected by the units of measurement, which is fine, as long as we keep the units of measurement consistent. Okay, so we've got the standard error of the estimate divided by n minus 2 square root is going to give us a standard deviation metric for this regression line that we've created. Explained variation. Remember 5 minutes ago I showed you the graph, said some of this is explained, some of this is unexplained. All right, we want to do the same thing with the explained. We want to take the square of each piece that is explained, and we want to add them all together. And that is going to give us the sum of squares of the regression. Think of that in terms of how much this regression line is explaining. SSR. How much the
Predicted values of y of the estimated regression equation deviate from the average y. Does that make sense? And then, of course, we've got total variation. Same thing. We don't just add up the total. We square the total because we want it in like units when we compare it to the error and the regression. So the deviation from the actual values of y and the average value of y. Sum that all up. Measure of error involved in using the mean to estimate y. Relationship among sums of squares. All right, check this out. The sum of squares total equals the sum of squares regression plus the sum of squares error. That makes sense, right? So the amount of error plus the amount that the regression explains is the total. All right, and now we are at the point I jumped ahead to because we had it based on our discussion, and I didn't want to wait too long before we got to the punchline. R squared, coefficient of determination, explained variation of y divided by the total variation of y. Mathematically, we will take our sum of squares of the regression divided by sum of squares of the total, which is this. And that's going to tell us percentage of the data that is explained by our regression line. Goodness of fit. I mentioned it is between 0 and 1. Measures the variation in y that can be associated with x. Everyone good there? Coefficient of determination. There's one other performance metric, which is the correlation coefficient, which is simply the square root of r squared, also known as r. So we take the square root of r squared, we get r. Simply take the square root of the sum of squares of the regression divided by the sum of squares of the total. Remember, these were all squared sums. Sum of squares of the regression, sum of squares total. So r just unsquares them. And it tells us not exactly how much of the data is explained, but higher indicates a stronger relationship. Not only that, or I should say further from 0 indicates a stronger relationship, because the r can be positive or negative. The r squared is always positive because it's just a fraction of the whole. The r can be positive or negative. And in the example we were using, we were suggesting that the time you spend online is going to positively influence the amount of money you spend online. So we're saying there's a positive relationship. It could be a negative relationship. Right? People who spend more money, more time online, maybe that just means they're playing video games the whole time. So the more time people spend online, those folks might spend less money online. Could be negative. And the R, coefficient of determination, the R, correlation coefficient, will tell us that. All right. Good. So this is what we've done so far, I guess is part 1, performance metrics. We constructed this regression line, and we used some math to determine how dependable, how accurate, how much this independent variable explains the dependent variable. What I promised you we would do next is talk about what we can infer about the whole population. Because this is just a sample. That y-intercept, or the slope, what does the whole population say about that? Or how can we relate that to the whole population? All right, so we're actually taking a sample and developing an estimated regression equation, an estimate for the true line if we use the population. Okay. The regression model, y, which is the actual dependent variable, say money spent online, is going to be the population, y-intercept, plus the slope times x, and there's going to be a certain amount of error in this term. The couple things that have been introduced here. Oh gosh. Okay. This little alpha sign is the y-intercept of the regression line for the whole population, and this big cursive B is the slope of the regression line for the whole population. We'll talk about the error term in a minute, but I just want you to understand we've switched terms to talk about the whole population. Now, I apologize for this, but does anyone recognize this term? What do we also know about this term being used for? Significance level. All right, so we're just going to have to learn to live with that. Statisticians use that two ways: the y-intercept and the significance level. For now, we're just looking at y-intercept. And I don't think it'll be a problem. I would never give you a question designed to confuse you on that point. Now, we're going to do a few things. One, we're going to say, well, our sample gave us a certain y-intercept. What happens if we look at the whole population? Well, we're going to have to develop a confidence interval for our y-intercept to determine what we think the actual population y-intercept is. Same thing for the slope. We determined an upward sloping relationship of slope of 1.5. What would that be if we were to sample the whole population? Take the data from the whole population. Well, there's going to be a confidence interval. We're going to determine how big it is. And we're going to give an estimate based on the information we have. We're going to do those two things in a minute. This error term is what we talked about at the beginning of class. Emeka and Ishu both spend 14 hours online, but they're different people. Emeka spends a certain amount, Ishu doesn't spend quite that much. Because there are other things that explain that. We can't approach an exact number because of the differences in the population. This graph illustrates this. So we've got an independent variable, maybe time spent online, and we've got a dependent variable, maybe money spent online. We've got a population, y-intercept. We've got a population slope. Now, if you look at all these points of data, let's assume these are individual people, it looks like there is a strong relationship. We could use the math to calculate the equation, for this line, but just looking at it, there's a strong relationship there. So let's factor that into our business decisions. But based on differences, there are divergences around this estimate. And that's what the error term is in the previous slide. We need to understand that. So calculating an exact value, all right, an exact value of how much money Carlos spends online, given what we know about our other points of data, we need a wider interval for that. But what we can calculate with some degree of exactness is the expected amount. The expected amount that Carlos will spend online. Let me pull up this slide and see if and let that sink in. So, the expected amount that any individual spends online, given how much time they spend online, is going to equal the population intercept plus the population slope times x, the amount of time they spend online. Now notice we've dropped the error term because now we're just calculating the expected. We're calculating this line, and we can calculate this line. It exists. In reality, there is an exact number. If we were to ask every single person how much time they spend online, how much money they spend online, we could get this exact line. The expected amount they spend. If we want to know the exact amount they spend, well, we just can't tell. We're going to have to use a normal distribution to account for that variation. And we're going to have to add that error term. But expected, we can get it right on. Of course, we're taking a sample, so we have to use confidence intervals. Does that make sense? In terms of the expected value of y and the actual value of y. Make sense? All right. All right, so let's think about how we want to do that. Estimating the slope and the intercept. Okay. Let me actually go back to this graph. So if we were to take a sample, we could estimate the y-intercept. Say we had 6 points of data, we would get a y-intercept based on that sample data. If we were to do that again, another 6 people, we get a different y-intercept. We do that again, another 6 people, another 6 people. We do that 10,000 times. We would put all that information in frequency distribution. What would that frequency distribution look like?
Normal distribution.
Normal distribution. Okay, so there's a normal distribution around here. Fine. Similarly, for the slope, we get sample after sample of 6. We get a normal distribution. That normal distribution would have predictable qualities. We could say that the normal distribution will have the population y-intercept at its center, and it will have a predictable standard deviation. Similarly, the slope, if we were to do this over and over again, would have a normal distribution with the population slope at the center, and it would have a predictable standard deviation. So these next 4 or so slides, I'm just going to repeat that information. Okay. So sampling distribution of the sample intercept. So we take sample after sample of 6 or 30 or however many we take. The sample intercept has a normal distribution. At the center is the actual population sample intercept, and it has a standard deviation which we will have a formula for. So now we can say this is what we got, and we can give you a confidence interval based on the assumption that it will fall into a normal distribution. Normal shape, center value equal to the value of the population. A, remember we used A for the sample y-intercept, and now we're using the sigma term for the population y-intercept. And of course, the standard deviation can be estimated. We'll get an equation for that in a minute. Okay, sampling distribution of the sample slope. All right, so we've taken a sample, we come up with a slope. If we do that over and over again, that information would fall into a normal distribution with predictable qualities. At the center of it would be the sample slope the population slope, and it would have a standard deviation that is predictable, estimatable. We have an equation for. All right, same thing. Normal shape, center equal to the population, standard deviation that can be estimated. Okay. So now I'm going to give you 2 formulas for standard deviation. One is the standard deviation for the sampling distribution of sample y-intercept. The other is the standard deviation for the sampling distribution of the sample slope. Let's just repeat that again, because we shouldn't be scared by those terms, right? We've heard that long standard deviation of the sampling. Yes. We've heard it over and over again. So I'm going to give you 2 formulas for standard deviation. One is the standard deviation of the sampling distribution of the sample intercept, and the confidence interval, and then I'll skip ahead to the next slide. The other one I'm going to give you is the standard deviation of the sampling distribution of the sample slope. All right, we're not scared by those, are we? We're scared. No way. Why would we be scared by those? All right, let me go back to slide 30, and let's break this down. So, the standard deviation of the sampling distribution of the sample intercept, we'll notate with SA. Remember, A is the sample intercept that we are using, because we've got sample data to estimate the standard deviation of the sampling distribution of the sample intercept. This is the sy dot x. This was the standard error of the estimate. The you cast your mind back to 15 slides earlier, remember this was the sum of squares error divided by n minus 2 and the square root of that. Alright, I'll stay sane if you will. Times some other junk. The square root of the sum of all the x's squared times n, number of samples, sum of all the deviations in the x's squared. This little x bar is the mean x, the average x. I don't really need to break that down and think about what it means, other than just try to crunch it out once, maybe twice, get a sense of where the numbers come from, and then after that, we'll look on you, the printout, to tell us the information we need. For now, I just want you to recognize this is the standard error of the estimate, which is that thing we learned about 15 slides ago, times some other stuff. And of course, we want confidence intervals. When we're using small numbers, in the examples in your textbook, they're all small numbers. Sample size of 6, sample size of 10. We're going to use the t statistic. But we can use the t statistic because there are assumptions of normality. We know that the sample internet, if we were to calculate that 1,000 times, it would fall into a normal distribution. And I said sample internet, I meant sample intercept. And the sample mean would fall into normal distribution, so we can use the t-stat. So what we get from the sample intercept plus or minus the t times this standard deviation. So A is the sample intercept plus or minus the t statistic times this standard deviation, which we are fortunate enough to be able to predict. Right, Geese?
Sure.
All right. So one more time. What is this? This A
Sample intercept.
plus or minus. What is this?
T.
Yeah, we're going to look in the back of the book. T with n minus 2 degrees of freedom. And what is this?
Standard deviation.
Standard
Standard.
Yeah, you got it. We're going to do this exact same thing with the slope. Same thing, just slightly different definitions. Slightly different way of describing it. You ready? Let's do it with the slope. Estimated standard deviation of the sampling distribution of the sample slope. I'm throwing in this sampling distribution of the sample slope. Your textbook didn't word it quite like that. I don't know exactly why, but so sometimes it's not worded like that. But I'm going to say estimated standard deviation of the sampling distribution of the sample slope. Standard deviation, or that slope that we're going to construct based on our sample data, is going to be the standard error of the estimate, which is the thing we learned 15 slides back. Sum of squares error divided by n minus 2 square rooted, divided by some other junk. All right, once we construct this, we can say, gosh, based on our sample data, we have a slope. It's upward, it's positive. So I'm going to tell you that the more time you spend online, the more money someone will spend online. It's related. So let's target all the people who spend time online and try to sell them our products. But I'm not sure of the exact slope. I've got a standard deviation figure based on if I were to do this thousands of times, and it's this. So I'm going to tell you my estimate for the slope, plus or minus, based on my confidence interval that my company is comfortable with. So B is our estimate for the slope based on sample data, plus or minus the t statistic, times standard deviation for the sampling distribution of the sample slope. Which one?
X.
This standard error of the estimate, this is the term we learned 10, 15 slides ago, which was the standard deviation figure for the line of best fit. I have to do, whenever I say line of best fit, I always have to do this. Okay, let me questions? So I think this was the end of part 2. All we need is that third thing I promised you, which was when we're looking at actual values of y, how do we estimate that based on personal differences? Oh wait, forgot hypothesis testing. All right, this is simple, easy stuff. So remember I said a minute ago, when I constructed this data, estimating how much money someone's going to spend online versus how much time they spend online, I'm going to come up with a slope figure. All right, I think it's positive, but it may not be positive. It might be 0. There might be no relationship. It's possible also it could be negative. So I want to determine how confident I am that there is a positive relationship. And how we're going to do that is with a hypothesis test that starts off by assuming that there is no relationship. So I might say the null hypothesis is that the slope is a straight line. Amount of time spent online, amount of money spent online, no relationship. You could spend however much time you want to spend online, it's not going to increase the amount of money you spend. That's a straight line, no relationship. I'm going to use that as my null hypothesis. I'm going to gather some data, and I'm going to determine whether or not I find overwhelming evidence to say that is not true. I have found evidence that shows the slope is so steep, I'm going to reject the null hypothesis that the slope is 0. Or I have found evidence to show that the slope is so steeply negative, I'm going to reject the null hypothesis that the slope is 0. Does that make sense? So as I recall, these next little paragraphs are just a way of summarizing that. We need to set up a hypothesis test to determine formally whether the sample data we've collected makes a compelling case that we found a useful relationship. Our useful relationship would be more time online because more money online. All right, if that's true, then that helps us in our business decisions, perhaps. To do this, we will test whether the value of the slope b, right, this is population slope, is 0. So, null hypothesis, the slope in the population equals 0. Alternative hypothesis, the slope in the population does not equal 0. Let's gather some data, see if we can disprove the null. The slope is key. All right, if the slope is 0, the variation is unconnected. So if we can't disprove this, then we don't have useful information about determining how much money someone's going to spend online. Does everyone understand this? So if this slope is 0, we might as well have not sat through this class. And you may think you might not have well sat through this class anyway. But hopefully one day you'll find something where you say, wow, there is a strong positive relationship, and I know how to explain why, and I know how to use it for an effective business purpose. The y-intercept is not as critical. If we're able to define a relationship, positive or negative, more often than not, that's something that we will get excited about because we'll be able to use that information. On the other hand, if it is not 0, the sum of the variation. Yeah, so if it's not 0, sum of the variation can be estimated or explained. All right, test statistic. All right, what is the test statistic that we're going to come up with? And you may recall from last time, overwhelming evidence, we need a significant test statistic. We are going to use the t distribution because we're using small samples in this chapter. B is the sample slope that we construct from our sample data minus 0. We're assuming that it's 0, so we're saying there's no difference between the slope and 0, and we're going to divide that. This SB, what is this?
Standard deviation of this sampling distribution of the sample.
Yes. Yeah, I think I heard all that. The standard deviation of the sampling distribution of the sample slope. So it's the standard deviation measure we use for our estimate of the slope. So I had these 6 points of data. I came up with an estimate for the slope, all right, and I'm going to use the standard deviation for that slope. And you may recall in constructing that standard deviation, there are a couple different pieces to it. Decision rule, critical values approach, reject if the t-stat is less than the negative t-value or the t-stat is greater than the positive t-value. So we might look at the degrees of freedom and say for 95% confidence, our t-stat, or t-critical value is plus or minus 2.2. And if we get an extremely negative, we reject the null and say there's a negative relationship. If we get an extremely positive critical value, we reject the null and say that there's a positive relationship. Alternatively, we could use the p-value approach. For t, you're going to need to use Excel to calculate the p-value. The p-value tells us the probability of finding a result at least that unlikely. At least that extreme, excuse me. The probability of finding a result at least that extreme. So a low p-value says, gosh, that was really unlikely to happen. And if the p-value is below our significance level, then we reject the null and say, that was so unlikely to happen that I'm going to say, reject the null, that there's no relationship, and say, yes, there is a relationship. Makes sense? Okay. Rejecting, okay, this is just some fine print. Let's talk it through. Rejecting the population slope is zero, null hypothesis, including the relationship between x and y is statistically significant, does not enable us to include that there's a cause and effect relationship. Remember, we can't say one thing causes the other. All we can say is there's a relationship and a correlation between two things. Rejecting the null does not mean there's necessarily a linear relationship. But it does mean that there's a linear relationship in the portion of the data that we sample, which tells us something significant. So outside of the data we sample, maybe the relationship is not a straight line. But within the data we sample, we can say there is a linear relationship that explains part of the variation. So we do say linear relationship, but just keep in mind there is a sample there's a sample space beyond that we want to be careful about making assumptions for. Okay, last piece, estimating values of y. Now remember, we can use the data that we conduct or collect to estimate an expected value for y. And we can estimate that, in theory, right on. We're going to need some confidence intervals because we've just taken a small sample, but in theory, we can get to one exact point. In reality, what is it? Something? What happened? Did I say something wrong? Oh, no. No, okay, all right. Sorry. In reality, there's going to be differences in the population. So we can't say with that same degree of certainty that if you spend this many hours online, you will spend exactly this much money. So estimating expected value for y. Oh boy. All right. So this is an expected value for y. Now, this y hat, recall, that is a predicted value for y. Remember, we constructed an equation. We said if you spend 14 hours online, we predict that you will spend $75 a week online. That's y hat. Okay? But we're going to need to add a level of confidence, or add an interval range to that estimate. Let me put this away for a minute. Put that equation away for a minute. Now remember, there were different components to our standard deviation estimate. There was a standard deviation for the y-intercept, and then there was a standard deviation for the slope. Question is, how do we combine those two so that we can determine the right confidence interval for our expected value for y? So let me just repeat that same thing again. So we've constructed a regression line based on best fit line, and we have a prediction for y. We say if you spend 14 hours online, you will spend $57 a week. That's our point estimate. Question is, how big of an interval do we need to be 95% confident, be 90% confident, 99% confident? And in terms of the variation in that, there are two things that we've talked about. One is we may have gotten the intercept wrong, and we need to establish a confidence interval for that. The other is we may have gotten the slope wrong. All right? Is it this steep? Is it this steep? What is it? So how do we combine those two? And the answer is that formula. It's really all you need to know about that formula. That's combining all the different elements of variability to give us the right confidence interval. Fair enough? So, this is another one. I would suggest you work through a few times. Maybe try this one a few more times than the others. So, a particular x value, so say 7 hours online, the predicted value for y is going to be plus or minus. We're going to use the t statistic. This standard error of the estimate. This is what you learned 20 slides back, which was the sum of squares error divided by n minus 2 square rooted, times some other junk. 1 divided by n. So the larger the sample size, that's going to make this figure a little bit smaller. One noteworthy thing. The actual value for x, or the value for x that we're inputting into this equation, which we said was 11 or 7, whatever it was, minus the average value for x squared. And that's not a sum on top. It's just those x's. Divided by the sum of every x value minus the average x value squared. Okay. One last piece. This is going to give us expected value for y. So I mentioned earlier that we have differences. Some people will spend more money because that's just who they are. What if we want to calculate the actual value for y? I want to know exactly how much money Carlos is spending online, given that he spends 13 hours a week online. I need to widen this interval just a little bit. Because I can get, specifically, in theory, I can get exactly to the estimated value for y. But to know exactly Carlos as an individual, I need to widen the interval just a little bit. So we use an equation that is just a little bit bigger. We add 1 under the square root. Now, hopefully this will be a relief to you. I didn't ask you to do any of the homework problems for this particular one. I just want you to be aware that if we're looking for a specific value for y, we would widen it a little bit. If we want the estimated value for y, we use the equation on the previous slide. All right, how's everyone feeling? Okay, so what I'd like to do is take a quick break. After the break, I would like to go through some examples, some exercises. If you feel like you've got enough already, then you could go home. That's a possibility, but I would suggest you stay. I'm not going to throw any more complicated information at you. I'm just going to go through the actual exercises in the book. And my plan is to go through the exercises like 11.1, 11.2, where you have all the answers there in front of you, so you can reflect on them this week to make sure you're comfortable on that. So let's come back at 8 o'clock, and let's just ingrain this a little bit more. What happened? What?
last week, my test submitted.
Yeah.
That got submitted accidentally and it was complete.
Yeah, did I reset it? I reset it,
No.
didn't I? I didn't reset it?
Like,
I told you I was going to reset it.
Yeah,
I
I
didn't.
sent you an email.
I told you the same thing. Yeah, you sent an email.
Oh,
But I
you-
told you at the end of the class I was going to reset it.
Yeah, you did.
I told you that when I lied to you guys, right? That's what you're saying.
I don't know.
There's
Things
three.
happen.
There was
No.
you two, and then there was you. And I didn't reset yours either.
I think you reset the wrong one.
I think so
Quiz number 2
too.
was has no score on it, but it was
I didn't check.
Oh gosh. All right. All right. So
Yeah, you might have reset them.
That means I gotta do number 2 also.
did I
Since I
reset
feel like
two?
on phone,
Are you
but I-
two?
Yeah, but I put on two.
I gotta check.
Do it over.
Did you really?
Yeah.
Okay. All right. So I just
Three is
reset
the
the
one.
wrong one.
I'm not sure if you did it that often. I didn't check this, so I know I checked
Okay.
3.
Yeah, no, I clicked on each
So
one.
what do we do
I
now?
clicked on one, I'm okay.
Do you want to take?
Click on two.
Do you want to take two again? Is that
No.
okay?
I guess.
You could just tell. You could just tell me what you got on. What score you got on two.
I think I was off by like 1 point on that
You-
one.
you-
It's
all right.
number 3. I just.
You all got two 100% correct. Right?
See that?
Right.
I
Trust
was a
God.
little alone too, but I actually have to do it one with the
Okay.
I don't want to put my time.
Okay,
Just
alright.
wanted to let you know.
All right. So I'll
Number
reset. I'll reset 3 for the 3 of you because of technical
What
difficulty.
about 2?
Why don't you? If you want to take it, take it. If you don't, just remind me that you got a perfect score at the end of the quarter. Okay.
Yeah. Because, I mean, it's like, he wants to sleep. Do that again. I did another class, but this one I just did fresh. I was almost done with it.
Oh, you mean this week's one? No, it was you do.
I usually just submit it.
They're due before the following class. So you're like a week ahead. I'm also saying I know what I did progression before. It wasn't easy and not leaving class at all. That's for sure.
I mean, on Excel, it's
On Excel, it's so easy.
pops up everything, but when I did it, when someone was like, "Oh, just you gotta like, do something there," I didn't know what any of those things meant because I didn't read the chapters. I had to go back and it explains everything. Like, you know, like, this is what this is. This is R2. Oh, okay, it's like
And I'll tell you this, I'm going to do it, and I'm going to add additional codes later. I'm going back and doing a lot. I've been doing a lot of this work twice, just to kind of make it easier for me to remember.
the thing that gets me mixed up with the quiz is like when you answer it, and then like I don't know how to go to the answers. Like I start typing stuff up. Like, I didn't do the bad at this one. Like I got the last one. I got the rejection right, but the actual T stat thing I got one. About that.
I actually was very surprised how I did them last week. I did much better than I thought I was going to. I did not see that before. this is impossible to do by hand all the time.
Not all the time. We learned this in
Yeah,
operational
I know
math.
that's the class that was absolutely murderous.
Right, but
He made me tap everything away in the calculator. I hated my life, and then like
who did
at
you
the
have?
end, he's like, "Do this."
Who did you have?
Uh,
Giuliani?
no, it's the other guy that was doing it. He was really good, but he
Right.
making me tap it away all completely on the calculator, and then later on showing it how like, "Oh, you just do this in Excel," and I'm like,
But aren't you grateful that you know how to do it? Like you have a backbone.
I mean, it's
of it?
It's good to understand the math behind
Right.
it all, but I mean, at the end of the day, if I could just do it
You're
like
not
that
gonna-
too, I don't want to.
Right.
I mean, isn't that what the benefit of the computers in the first place is?
Correct.
But
Correct.
it's more about, I guess, drilling it into your skull and then knowing how to ensure you're putting it in correctly.
Which I'm okay with not having to do.
Benefits of the modern world.
Oh, that's
All right, let's start with some exercises. Let's turn to page 397. Let's do exercise 11.1. Finding a least squares line. In other words, we're going to calculate the actual. What? 397. 397. We're going to calculate the actual regression line based on the data points. So we would expect that an investor's risk tolerance will affect the investor's investment decisions. So for a simple linear regression analysis attempting to link risk tolerance to the percent of financial assets that an investor has invested in the stock market, the following data for 4 active investors are available. Okay, so we've got investor 1 through 4. We've got risk tolerance score, and we've got percentage of assets invested in the stock market. So let's take a look. For the low risk tolerance score of, say, 6, investor 3, see how that investor had 40% of assets invested in the stock market? Maybe the other 60% in a savings bond, something safe. And the high risk tolerance of 14, 70% invested in the stock market, more aggressive. So we look at those numbers. Initially, we think there might be a linear relationship. So how are we going to calculate this regression equation? So we want an equation. We want a y equals the y-intercept plus slope times risk tolerance. How do we do this? We go back to slide 8 or 9, where it gives us those really long, ugly-looking equations. Let's see. I may be able to find it first. I'm going to look at slide 6, or page 6, slide 12. This gives us everything we need, right? And I did this by hand. The homework I assigned you, I promised that I told you last week that I actually do that, and I did this calculation by hand for, I think, question 2 and 4. I'm going to do it right now or show you how we would do it on Excel. And then after you've done it a couple times, you'll never ever have to do it again because you have a better understanding of where these numbers come from. You can just read the computer printer. So let's solve this problem using those equations on slide 12, page 6 of the handout. So I've punched in the risk tolerance score. We've got investor 1 has 12, 2 has 8, 3 has 6, third one has 14. And then we sum that. Just use a simple sum function in Excel. And we put in the percent of assets invested in the stock market, Y, 60, 50, 40, 70. Sum that. Use a simple sum function in Excel. The other things we need to solve this equation, you can see we need x times y. We also need the sum of x, the sum of y. We need the sum of x squared, and then I guess the sum of x again. So we just crunch those into an Excel template. So we've got x times y. So this is 12 times 60 is 720. 8 times 50 is 400, yada, 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 yada. And then we take the square of x. 12 squared, 144. Boom. We've got everything we need. All you need to do is crunch that formula to get the slope, and you would get 3.5. And again, what I'd recommend you do for one or two of these problems is just put these numbers in Excel and then just practice calculating the formula for slope. And in this example, you would get the formula for slope to spit out 3.5. Once you have the slope, you use that next equation on slide number 12. The intercept is the average y minus the slope times the average x. Same thing here. Excel very simply allows you to calculate the average x of 10, the average y of 55. So if you look at the calculations on page 397, average y is 220 minus 4, which is 55, minus b, which we calculated as 3.5, times the average x, which is 40 divided by 10, which is 10. And boom, we've got it. The bottom of 397, you've got a regression equation. The predicted value for y is 20 plus 3.5x. And if I were to ask you, if an investor has a score of 10 on the risk tolerance scale, how much would you predict that investor has invested in the stock market? Well, you would plug 10 into that equation. 20 plus 3.5 times 10. It's going to give you 55. Make sense? We'll move on to the next one. See everyone looking down intensely, so I'll wait just a moment. Slide 12, page 6. Yep. Move on. Exercise 11.2, page 402. This is the standard error of the estimate. This is the S subscript y dot x. So remember initially we calculated this line of best fit and we said that there's some error based on the sample data for that, and that's the standard error from the estimate. Later we added the fact that this is just a sample and not the whole population, So we need some variance on the intercept and some variance on the slope. But this was part 1 of 3 of standard deviation. The standard error of the estimate. And it can be, and it is illustrated on, let's see, where is it on the slides? Page, what, 9? Page what? Page 9. Okay, it's on the bottom of page 9. Fantastic. All right, the standard error of the estimate, S subscript y dot x, is the sum of squares error divided by n minus 2, and take the square root of that. And remember, we use the sum of squares error to find the best fit line, and we want the sum of squares error to be as small as possible. But there's still going to be some error, some leftover error, so that's going to tell us some possible variations in any hard predictions we're trying to make. So, exercise 11.2 on page 402 asks us to find this figure. So, we're doing the same thing, risk tolerance, and the correlation to percent of financial assets that an investor would have invested in the stock market. The estimated regression equation for the least squares and data table are shown below. We need to compute the standard error, sum of squares of error, and the standard error of the estimate. Okay. So, let's take a look. I have put that up on the Excel sheet. Make this a little bigger. Okay. So we've got, all right, so we've got our X's. All right, our investor 1 had a risk tolerance of 12 and had actual 60% invested in the market. And then a moment ago we constructed the regression equation, right? It was 20 plus 3.5 times X is going to give us our predicted value for Y. So this is Y hat here. We've got the regression equation because we just crunched out the math on exercise 11.1. And now we have a predicted value for Y. But we can't predict this data perfectly. In fact, you can see that for investor 1, here he has 60% of assets invested in the market, and we predicted 62. So we were off by 2. For investor 2, we were also off by 2. The other direction, though. Investor 3, we were off by 1. Investor 4, we were off by 1. Now see how these all sum to 0? So we've got the line of best fit. The unexplained variation sums to 0. Yes, line of best fit. So all lines of best fit will have a sum of squares, will have a unexplained variation of 0. But I use that example, they could be off significantly and they just cancel each other out, where the sum of the unexplained variation is 0. So we take the squares of all of these numbers. And it's actually really interesting here. This, we've got one, we're -2, the other is +2. One is -1, the other is +1. So they are exactly off. One is off by 2 and it's high, the other is off by 2 and it's low, the other is off by 1 high, the other is off by 2 low. So they're going to sum to 0. But you can see we could replace here. This could be -20 and this could be +20, and they would still sum to 0. So we need information about how much that dispersion is. So we take the square of all those. So -2 squared is 4, 2 squared is 4, -1 squared is 1, 1 squared is 1. We add that all up, we get 10. We divide by n minus 2. There are 4 items in this sample. Divided by 2 is minus 2 is 4 minus 2 is 2. So 10 minus 2 is 5. Square root of 5 is 2.24. So our standard error of estimate, 2.24. As you can see at the top of page 403. All right, ready to move on? Let's do it. Let's move on to exercise 11.3 on page 407. All right, we're still using the risk tolerance example. And now we want to calculate the R squared and R values. So let's remind ourselves, what is R squared? Yeah, you're on the right track, Daniel. The percentage of variation, yes, that is explained. Yes, R squared. Measures the percentage of variation. What page is that?
11.
11. Fantastic. Page 11. Yep. All right, so we've got R squared, which is the sum of squares of the regression, which is the explained variation, divided by the sum of squares total, which is the total variation. And then we take the square root of that and we get R, which also tells us a goodness of fit estimate. And an R tells us positive or negative relationship. All right. So let's take a look, exercise 11.3. We're going to need some pieces of information here, in addition to what we calculated in the previous examples. Make this bigger if necessary. Okay. All right, so we've got investor 1, 12 is their risk tolerance. Their actual investment in the stock market is 60%. We predicted that at 62. So the first thing we need to calculate, so we need two things to calculate R squared. We need the explained variation, and we need the total variation. All right, so how do we get total variation in Y? All right, so these are the Y's, 60, 50, 40. So let's just look at the average. In the Y's are percentage of assets invested in the stock market. So if we average all these four, then from our sample we've got the average investment in the stock market. All right, the average investment in the stock market, 55%. Boom. So total variation is going to be this 60 minus 55 is 5. So this person has 5% more invested in the stock market than average. Right? We haven't done the regression equation yet. We're just calculating total variation from the straight up average. And it's 5% more. We take the square of that, and we've got our first total variation squared. We do that 4 more times, and we've got the sum of squared total variation. Sum of squared total variation. This person here has 50. The average is 55, so off by 5. Square it, we get 25. This person here is 40. Boy, that's way below average. Square it, that's 225. This person here is 70, way above average. Square it, it's 15 above average. Square it, it's 225. Now, we haven't gotten to the fact that we can explain some of that variation with our regression line. All we're looking at now is the total variation. So, sum of squares, total variation. Now let's look at the explained variation. Square it, and that's going to give us the sum of squares regression. Total variation that we can explain based on our regression. So for that, all right, we've got an investment. Investor 1 has 60% invested in the stock market. We predicted 62. So, okay, oh yeah, right. So we predicted 62, and the average, wait, what is this? This is the average, somebody help me out, what is this? This is the average, the predicted minus, oh yeah, okay. Okay. So the amount we predicted was 62. The average was 55. So we explained 7% difference. That 7% difference from the average of 55 to 62, we explained with our regression equation. Sorry, I hope I didn't confuse anyone with my lengthy explanation there. Square 7, yeah. So we're looking for the explained variation. Same thing here, except on the other side. What is we predicted? So we predicted. For some reason, this is not going in my head the right way. We predicted 62. The average. Oh, okay. Oh, yeah. All right. Yeah. So the average is 55, and we said, you know what? Based on that person's risk tolerance, we have an explanation for why this person would be up to 62. We can show you a regression line that says this person will have 62%. And we're off by a little bit, which was unexplained. But our explained is 7%, square at 49. Okay? Same thing here. We're off by more. Actually, we can explain more. Because this person has a really low risk tolerance, and they are more deviant from the average. But we can explain that. Square it, we get 196. Square it, we get 490. So, what we do now is we take the explained variation divided by the total variation. Explained is 490. Total is 500. So 490 over 500, that's a pretty good fraction, right? 98%? Yeah. So this regression equation explains 98% of the variation. So that would be a pretty good piece of information to know about someone. Yes?
Just I have it clear on my head. Total variation. To find total variation, we were taking the y-intercept, which were given, and we're subtracting from the average of the y-intercept.
So total, not the y-intercept, the average y. So the y bar is the average y. And we found in this example the average y was 55. And the total variation is going to be how far this actual investment in the stock market is from the average. And in the first one, that's 5. And then we square it, and we get 25. All right. So 490 over 500 gives us an R squared of 98%. Yes. Take that to your boss and tell her how much you know about the clients, how much you can predict about the clients before you even sit down with them. To get R, that's another measure of goodness of fit. It's the square root of R squared. And what's the great thing about R? What does R tell us that R squared does not? Nadina? Nadia? Yes, it gives us positive or negative. So is there higher risk tolerance means more investment, or does higher risk tolerance mean less investment in the stock market? And in this case, it is positive. So the higher your risk tolerance, the more you're going to invest in the stock market. And this is, wouldn't it be great if all of our data worked out this way? Where we have a 98% explanation of the data and an R of 0.99. Okay? All right, let's move on to the next exercise. 11.4 on page 414. All right, confidence interval. Build a confidence interval for a population intercept. So this is a new example. So we want a 95% confidence interval for population intercept term in the population slope. For our mobile apps example, explain what these intercepts, these intervals represent. So this was, if you look at the x and y's, I'll pull them up and I'll just explain what they meant by the x and the y. Exercise 11.4. Okay, so these x variables, these were websites that mobile app designers were linking their apps to. And this y variable, the dependent variable, is the number of times their app was downloaded. So developer 1 linked her mobile app to 20 different websites, and she had 600 downloads. Developer 2 linked his mobile app to 30 different websites, and he had 800 downloads. Number 3 was linked to 40 sites, 1,000 downloads. Number 4 was linked to 50 websites, 900 downloads. So it looks, just eyeballing it, the more websites you put your mobile app on, the more downloads you're going to get. There's some variation here. When we get up to 50, it went down. Maybe something else was going on there. So we don't have 100% predictive value, of course. And we are asked here to find the 95% confidence interval for the population intercept and the population slope. Now, there are 3 important terms for standard deviation. First, standard error of the estimate, which was the sum of squares error divided by n minus 2 and taking the square root of that. That was how good do we think that line of best fit is? Like, I really do have to do this every time I say line of best fit. How good do we think that was? That is the first standard deviation metric. Just based on the sample data, we know that we didn't get it perfect. We can't predict 100% just based on the sample data. And that is the standard error of the estimate. Sum of squares error divided by n minus 2, square root of that. 2 other important standpoints of standard deviation. One is the sample intercept was just taken from sample data. What happens when we take it from the whole population? Well, we just need a confidence interval for that. Second thing, slope. What happens when we take that from the whole population? Well, we need a confidence interval because we only have sample data and we're estimating, we're inferring what happens to the whole slope. Okay, and we are going to do those 2 separately. So let's pull up our slides where we're gonna get this information. We're gonna need the standard error of the estimate, which is I think what we did a couple problems ago. Let's just refresh. Where's the standard error of the estimate? That was on page 9. Okay, yeah. So put a little earmark on page 9 so you can flip back to that as necessary. And the second thing we need is the 15. Okay, excellent, thank you. 15 and I think 16 on the other side, they're going to give us, 15 is going to give us the standard deviation of the sampling distribution of the sample internet. I keep saying internet. Intercept. And on the other page 16, is going to give us standard deviation of the sampling distribution of the sample slope. Okay, so let's take a look at what data we need to get the standard deviation of the sampling distribution of the sample intercept on page 15. We need all the x's squared, and we need the difference, sum of the difference between x and average x squared. So let's just put that into our Excel. It's fairly easy. We just put the 4 points of data. Mobile app developer 1, developer 2, developer 3, developer 4. How many downloads? All right. We predicted value. Now this exercise we're actually given. We have a predicted value for y. And so we calculate all the predicted values. It's 400 plus 11x is going to give us our predicted value for y. And unexplained variation, we calculate the same way we did in the previous example. And we square it. To calculate the sampling distribution of the sample slope and sampling distribution of the sample intercept, we need some more information. This x variation squared, and we need the x squared. So the x, we just take the average of x, which is 35. All right, so this first one, 20 minus 35 is 15. Is 15 squared 400? Is that right? So this is, no, this is just x squared. This is just x squared. Yeah, sorry. 15 squared is 225. Okay, so is everyone with me here with these numbers? All right, x squared, the difference between x and, so this is 15 squared, so on and so forth. All right, now, so we're going to need to, first thing we want to do is calculate the standard area of the estimate, which is s subscript y dot x. That is the standard error, sum of squares error, which we can calculate as 27,000. Sum of squares error, unexplained variation squared, 27,000, divided by n minus 2. Take the square root of that. So standard error of the estimate is 116.2. And then we need to multiply that by some other junk, which you can see on page 15, to get the confidence interval for the intercept. So we multiply that by the square root of the sum of all the x's squared, divided by n, sample size of 4, times the deviation of x from the average x squared. We do all that, and we get a standard deviation of the sampling distribution of the sample intercept of 190.9. Say that with me one time. Standard deviation of the sampling distribution of the sample intercept is 190.9. And we want a confidence interval of 95%. And we know we're looking at 2 degrees of freedom. So let's turn back to our t distribution. Let's look at 2 degrees of freedom on the t distribution chart. And if we want a 95% confidence interval, we know there's a 2.5% chance we could be off by a really high metric. 2.5% chance we could be off by a really low metric. So we're looking at the area in the tails of 2.5%. So the t critical value is 4.303. Actually, we're not talking critical value. Critical value is more hypothesis testing, but we could call it critical value. It's the number of standard deviations we want to multiply the number of standard deviations we want to multiply by in order to get a 95%, to be 95% confident that the population sample intercept is within that interval. Yes, Mike? Why isn't it 3? We do n minus 2 because there's 2 unknown variables, the intercept and the slope. So more unknowns mean more estimating that is necessary. So we have a wider interval as a result, or we want a wider interval as a result. Okay. So we've got standard deviation of 190. We know that in order to encompass 95% of the data on a slightly flattened normal distribution, we need to take 4.303 of those standard deviations plus or minus. Our point estimate for the intercept is 440. But we know that comes with a standard deviation of 190. Now, if we just took one standard deviation, we would encompass approximately 68% of the data, right? Remember that discussion a month or so ago? Now, it's slightly different because t is different than z. But just so we don't lose track of where we are, if this were a regular z-score and we were to take one standard deviation, to plus and minus 1 times 190, we would be 68% confident. Plus or minus 2, we'd be 95% confident. Plus or minus 3, we'd be 99.7% confident. If it were z, but t is a little bit different, but I just want to remind you where we are. So to be 95% confident that we've hit the real, that we have the real slope, the real intercept within that range, we need to take 4.3 standard deviations. Okay, and what do we come out with? When we multiply our standard deviation by plus or minus 4.3, and then we add it to 140. What do we come out with for our interval for the intercept? All right, let me give you a hint. The answer is right at the bottom of page 414. Yeah, could be as low as negative 381. Could be as high as 1261. That's pretty wide. Okay. So let's do the same thing for the slope. So we have calculated a slope. What is the slope we have calculated based on our regression equation? Predicted y equals 440 plus 11x. What is our estimate, our point estimate for the slope of the relationship between sites that you're linked to and number of downloads? I'll give you a hint. It's one of those numbers. It's either 440 or 11. What is our point estimate for the slope of this relationship between number of sites that you're on and number of downloads? 440? Good guess. What is the slope? It's 11, right? So for every one additional website these developers put their app on, they're expected to get 11 more downloads. Right? So that is the slope. So it's a pretty steep slope. Color here. Maybe something like this. So 1 unit change in x gives us an 11 unit change in y. So one more app or one more website you link to will give you approximately 11 more downloads. That's what the regression tells us. So we're estimating the slope at 11. But there are two components of the standard deviation that we need to consider. One is what happened when we did the line of best fit. All right, we said there's still some error remaining. All right, it's the sum of squares error. Divided by n minus 2, take the square root of that, gives us the standard error of the estimate. That's one part. The second thing we said is, well, this is just a sample. What if we were to infer something about this to the whole population? We need a little bit of an increased interval for that. And I guess we're still on the same one. We're still on page 16 here, right? Now we're just doing slope. So the top slide on page 16, the small s y dot x, that's the standard error of the estimate, which is the sum of squares error divided by n minus 2, square root of that, divided by the square root of some other junk, x minus average x squared. So I recommend you take x minus average x and square it. So here we have x is 40, average x is 35, squared is 25. Simple, right? And then we sum all those together, and we get 500. So we find at the bottom of page 414, that SB, that is the standard deviation for the sampling distribution of the sample slope. And there are those two components, as we can see at the top of page 16. The standard error of the estimate divided by some other junk. And when we do that, we get 5.2. That's the standard deviation. So we have a point estimate of 11 for our slope. If you have one more website, we predict that you will have 11 more downloads. And we have a standard deviation for that estimate of 5.2. Question is, how many standard deviations do we need to add and subtract to that before we can be 95% confident that that interval contains the true population slope? What's that?
Check the T distribution.
Yeah, check the T distribution.
Just some.
Yeah, so we've got 4 samples. We've got 2 degrees of freedom. There's a chance we could not include in our interval something that would be really, really high. We could not include in our interval something that would be really, really low. But there's a 95% chance if we take 4.3 standard deviations, then we're going to include the true population slope. All right, our estimate was 11. All right, 1 over 11. Positive 11. And we calculate standard deviation of 5.2, multiply that by 4.3, 11 plus or minus 4.3 times 5.2. All right, we're going to stay on this one for just a couple more minutes because the slope is the key. Truly. How confident we can be about the slope tells us more useful information. So what's the answer at the top of page 415? What is our confidence interval where we can be 95% confident that the true population slope is between these two numbers. That's right. Negative 11.4 and positive 33.4. That's a pretty big spread, right? Now, a spread like that, I question how much useful information is in that spread. Because it contains three things. A negative number, 0, and a positive number. Remember, we just have a positive 11 for our point estimate. So what would it mean if there was a negative correlation? Going downward. So if you, what does that mean in practical terms? If you were to add one more website, you'd be losing downloads. Okay, that's in our interval. So the more websites you add, the fewer downloads you get. In order to be 95% confident, we have to say that that's a possibility. Now, what would a slope of 0 mean? No effects. Doesn't matter. And then a slope of positive is what we have. More websites equal more downloads. So our 95% confidence interval includes a negative number, 0, and a positive number. Now that's every possible number, or every possible inference we could make. It's not every possible number, but it's every possible inference that we might be able to make. The useful things we could say is there's a negative relationship, there's no relationship, or there's a positive relationship. And our interval contains all three of those things. So, we don't have any useful information here. Stay up all night, crank that out, say, I'm sorry, we don't have any useful information. and then your boss will say, well, of course it's related. And would I send you to that school and you just tell me there's no actual relationship? Like, well, confidence intervals, percentage, yada yada. Okay, any questions about that? No. All right, let's move on to, I believe, the next one, which is a hypothesis test. Yes. All right, this is on page 419. Testing the slope is 0 as a null hypothesis. Now, just to warm you up, in our last example that we just went over with the 11, if we were to conduct a null hypothesis test saying the slope is 0, we wouldn't have had any information to disprove that because there's nothing specific we can say, and there's certainly not overwhelming evidence of one direction or the other. But this is back to the first example we did. Page 419, exercise 11.5. In demonstration exercise, we're back to risk tolerance, percentage of financial assets invested in the stock market. Estimated regression equation was the predicted value of y equals 20 plus 3.5x. Student data shown below. Can we reject the null hypothesis that the slope equals 0 at the significance, at the 5% significance level? That is B, the sample-based coefficient for risk tolerance score, statistically significant at a 5% level? Okay, so remember we're talking about investor risk tolerance, and we're saying higher risk tolerance is going to make the client invest more. And you remember this one was a really strong relationship. It was 98% can be explained with the regression equation in a positive fashion. So we think there is some sort of positive slope. Higher risk tolerance equals higher investment. So let's set up a hypothesis test to determine how confident we are. Let's make the null hypothesis that the population slope equals 0. We think from our data initially that there's a positive slope, but let's just assume for a minute that the population slope is 0. And let's see if we get overwhelming evidence to prove the alternative hypothesis that the slope does not equal 0. So we're going to need a test statistic, a t-stat. is going to equal our slope minus 0, which is the difference. So the difference between the actual slope and 0 divided by our standard deviation, which is going to be what, this one, right? SB. All right. So let's see what stuff we need to do that calculation. So we need, so our B, our slope, I should erase this here. So this large B, capital B, is the population slope. But we have data for the sample slope. And what do we calculate for the sample slope? T-stat. What do we calculate for sample? It's just the regression equation. It's like 3.5, right? Yeah, it's 3.5. So 3.5 minus 0, the difference between 0, because we're assuming that B equals 0. We're going to see if we have overwhelming evidence to say that the difference between that and 0 is so significant. And we're going to divide by SB. So what do we need for, first of all, SB, again, is the standard deviation of the sampling distribution of the sample slope. And it contains two components. It is the standard error of the estimate, which is how well we fit that regression line. Plus, once we think of the whole population, how do we have to account for the difference between our sample and the whole population? And, yeah, we just did SB. Everyone's good? SB? All right, so we just need to find SB. So we need the standard error of the estimate divided by the sum of x minus average x squared. So for 11.5, let's see if I did this. What did I have? Yeah. Is that it? 40. Yeah, divided by 40. So that x minus average x squared added all together is going to give us 40. So the SB is going to be 0.354. 0.354. Okay. What does that add up to? T-stat. 9.89. 9.9? Okay. What we need now are, starts with critical, ends with values. Critical values. Okay. So we want to be, we're at the 5% significance level, right? So we could say, our definition of unlikely is 5%. So 5% we could get something really, really high. Or excuse me, 2.5% we could get something really, really high. 2.5% we could get something really, really low. If it falls in that range, we're going to say that's so unlikely that we're going to reject the null hypothesis. So we need a t-stat, critical value, for the 2.5% in the upper and lower tail. So we do the same thing we did in the previous exercise. We flip back to the t-stat. We find 2 degrees of freedom. We look for 2.5% in the tails. Boom, it just happens to be the same number, 4.303. So our critical values are negative 4.3 and positive 4.3. And our t-stat is way, way over there. Right? So we reject the null hypothesis. Actually, I think I'm done with this. I can just turn this off. And work on just a little sliver there. I think we're good here? Yeah. Excellent. On the last one, 11.6 on page 422. So expected value of y. So for our mobile apps example, construct a 95% confidence interval estimate of expected number of downloads for the set of all apps that have 45 linking websites. So if you have 45 linking websites, what do we expect your number of downloads to be? All right, so the first thing we need is our predicted value of y. And we know from the previous example that our predicted value of y, is what, 440 plus 11 x, is that right? Yeah? Okay. So what is our expected value of y if, our expected value of y if x is 45? So let's see, 440 plus 11 times 45, right? So remember 10 minutes ago or so we said every additional website you link your app to, you expect 11 more downloads. Equals, what do we get for that? You can either calculate it or you can just look on the 935. Okay. 935. Okay, so that is our point estimate, but we need to account for some variation to get a confidence level, right? And there's a number of levels of the variation. It's first, it's the goodness of fit line just based on the sample data. There was some lack of perfection there. I won't say problems, just lack of perfection, which is our sum of squares error divided by n minus 2. The square root of that gives us our standard error of the estimate. That's just from the sample data. And then there's the two components once we go from the sample to the population. Well, we could have been wrong with the intercept. We could have been wrong with the slope. So we need to consider SA, and we need to consider SV. And of course, I mentioned a minute ago, we need to consider SY given X. Okay, we need some equation that puts all three of those together. And when we first saw it, we're like, oh God, I don't ever want to see this again. But imagine trying to put all three of those together without that equation. So let's think about how that works. We know from previous work, what we did in the last example, that the standard error of the estimate is 116.2. And then we just need to take the square root of 1 over n plus the actual x of 45 minus the average x squared divided by the sum of x minus average x squared. Sum of squared x variations. Okay, so let's say that when we find that standard deviation, we're going to get, what do we get? It's 77.9, right? When we do all that, we get 77.9. Everybody with me there?
Yes.
77.9? So that is the term we're using for standard deviation. When we combine this plus this plus this, we get the 77.9 for this particular equation. The next question is, how many of these standard deviations do we need to add or subtract from our point estimate to be 95% confident that this point estimate contains the true expected value for y if x equals 45? So we want to be 95% confident. So we look at degrees of freedom, and we look at the t-table. And when we do that, same thing as before. 4.3. So we want to add 4.3 standard deviations and subtract 4.3 standard deviations from this. And if we do that, we're going to get the interval, and we're going to say the true expected value of y given 45 x's, and x at 45, is this interval. And what does it come out to? 599, 1270? Okay. 599, 1270. Okay, so keep in mind, this is the expected value of y. Expected value of y given 45. Don't get confused and think that this is saying anything about the true slope or intercept. So if I'm an app developer and I link my app up to 45 websites, I come to you because you've taken statistics, and I say, how many downloads do you expect me to get? And you say, I'm 95% confident you're going to get between 600 and 1,270 downloads. All right, you all are still awake, which I like. And I don't see too many pained faces, which I also like. I'm around to continue going over this. If you have questions about the quiz from last week, or anything else, we can go over that for at least another half hour, maybe longer if you want to. And I'll look for your question, Isha?
Yes. I have a question that I didn't get the grade for the assignment.
Okay, great. I'll take a look at that and see you all next week unless you have further questions. Oh, you didn't get a grade for your Excel? Oh yeah, I'm way behind on Excel. I'm sorry. Hopefully I'm gonna get caught up on the Excel grading tomorrow and the quiz grading tomorrow as well. And then I'm gonna reset quiz 3 for Randy, Lewis, and Dan Rand.